Hello and welcome to our 11:30 a.m. press conference, the declared North Korean nuclear tests on September 3rd, 2017. I'm going to introduce Dale Anderson from Los Alamos National Laboratory, who is going to introduce our speakers.
Thank you and welcome. Prepared just a few introductory remarks and a slide or two before we get going into the question and answer segment of the conference. On September 3rd of this year, more than 100 seismic sensors around the world detected an unusual disturbance in the vicinity of the North Korean test site, an underground explosion. The seismic magnitude was larger than all DPRK tests and the largest globally in decades. That the event was consistent with an underground nuclear explosion is something we were able to determine based on remarkable advances in geophysical methods. And today we're going to talk about some of these advances in more detail. But first, how do we know it was a nuclear explosion? Well, simply it's because history tells us so. Between 1945 and 1996, 5 countries, the United States, the Soviet Union, Britain, France, and China, executed about 2,400 nuclear tests. These tests provided scientific evidence that underground nuclear explosions could be detected and potentially analyzed with global seismic stations. The 1957 U.S. experiment, called Rainier, was the first fully underground nuclear explosion. Rainier was detected by about 50 seismic stations around the globe. However, it was confused as an earthquake by some. The international community then recognized the need for a global network of state-of-the-art seismic stations. It also recognized the need for scientific research to exploit seismic data so we could confidently monitor underground nuclear explosions. The science of nuclear nonproliferation was born. Today, the International Monitoring System, the foundation for the Comprehensive Test Ban Treaty, comprises 149 operational seismic stations, and we're working toward a total of 170. Additionally, there are currently 49 IMS infrasound stations, and we expect to reach 60. These stations provide an enormous amount of data that's analyzed by some of the brightest minds in the field, including those joining us today. And if I could draw your attention to the slideshow for a few moments to set the context for the discussion. How do I get to the next slide? Left, right? There we go. This places the context, the discussion today in some historical context. Importantly for the AGU and the U.S.A, Seismological Society of America, in 1992, the non-proliferation experiment, an underground chemical explosion to demonstrate global detection down to 1 kiloton, was executed. And from that, the AGU and SSA issued a joint position statement that the NPE, the non-proliferation experiment, provided confidence for global monitoring down to 1 kiloton. Now move to 1992, President George H.W. Bush declares a moratorium on all U.S. nuclear testing. In 1993, the CTBTO, Comprehensive Test Ban Treaty Organization, began sustained investments to stand up the international monitoring system and the International Data Center to provide high-quality products to those that have signed the treaty. In 1996, President Clinton was the first to sign the CTBT. In 2000, importantly, the CTBT member states determined that the IDC is capable of routine independent data analysis and product distribution. And then, of course, in 2006, we had the first DPRK test. And so that places the discussion today in some historical context. The next slide, and I don't know if I can control presume so. Oh yeah, I can. To pique your scientific curiosity, this is a simulation model of an explosion. Whoops, I gotta go back. There we go. On the left, you see the seismic wave. On the right, you see the energy from that seismic wave damaging the rock. And so in essence, we're talking about how that energy and how that signature gets out to a sensor. And the panelists here are a distinguished group of panelists. They're internationally recognized geophysical researchers in explosion monitoring. And so I'd like to introduce Dr. Thorne to my right from the University of California, Santa Cruz. Dr. Tormod Kverna, he is the head of R&D for seismology at the Norwegian Seismic Array. Dr. Young-Soo Jeon, a research scientist with the Korean Meteorological Administration, and Dr. Jolanta Kazmierski-Mikulik, the Atmospheric Sciences Officer for the Comprehensive Testbed Treaty Organization in Vienna. And finally, Dr. Jelle Assink, a senior geophysicist with the Royal Netherlands Meteorological Institute. And at that point, we'll open up the discussion. Well, let's see, we want to have some short presentations by the panelists up here. And Jelle, if you could come up and maybe give a brief presentation, talk on your research, and then we'll go to the formal presentations. And I'll sit behind you. Is that okay? Yeah. And then after they give their short presentations on the research, we'll open the meeting up to questions from the press.
So good afternoon. My name is Jelle Assink. I am a geophysicist with the Royal Netherlands Meteorological Institute, where I focus my time on seismoacoustic coupling. And to give you an idea of what this means is that if you have an underground nuclear explosion or an earthquake, the Earth starts to move and it starts to act like a giant loudspeaker, and it will emit acoustic signals into the atmosphere. So these are sound waves, but in contrast to what we are using every day, these sound waves are inaudible. So you need very special sensitive microphones in the so-called infrasound band to record these sound waves. So using these infrasound waves together with seismic waves, we are trying to tell something more about the source characteristics, for example, the source depth. And that is something that we presented on this week at the AGU.
I think we go to Dr. Lay, correct? Are you next? I thought, yeah.
I think so. If we can get to my slides. Okay, I'm a seismologist. I've been working on nuclear explosion analysis for almost 40 years now, since I was a graduate student at Caltech. And in the early days of my career, there were a lot of nuclear explosions being conducted and signals were available. But then, of course, since the moratorium, there's been very few explosions, only conducted by India, Pakistan, and now North Korea. And during the time, over the past few decades, the instrumentation around the world has grown immensely. So that this earthquake or this explosion in 2017 is recorded by thousands of sensors operating around the world, openly available, recording the ground shaking as a function of time. And those sensors, primarily deployed for earthquake studies, record the signals from explosions. We can then analyze the signals that are recorded to identify that this was an explosion. I won't talk about that. Beyond that, we can use the signals that are recorded to estimate how large the event was. And that's a very politically charged number because it's important to estimate what size of explosion the test demonstrates that the country is capable of. It's a difficult problem, though. What this slide illustrates is that you can have seismic recordings that record how the ground shakes. And basically, those are instruments that you can think of as like stethoscopes put onto the Earth's surface, just listening to any gurgling within the Earth. It could be an earthquake, or it could be a sudden abrupt release of energy from a volcano or an explosion or an impact. That generates sound. Sound propagates through rock. As the sound propagates, it shakes the rock. The instruments simply record the shaking as it passes each station. So the ground normally is not shaking that much, a little bit of noise from wind and other vibrations, and then there's a signal that came in. This is for an event many years ago recorded on analog systems, on the old-fashioned seismological drums that we used to have. And what you would measure is the peak amplitude of that. You correct for how far away you are, for the effect of the energy getting weaker with distance, the sound gets weaker. And you can measure the seismic magnitude. And then if we have a region which we have previously calibrated, we know the magnitude as a function of known yields. We have a magnitude-yield relation. We can plug in the magnitude we measure and estimate the yield. That's the standard practice that we implement for sites that we have knowledge of, where we actually know the yield and we empirically connect the specific known yield to a known or measured magnitude. So you need a calibration curve. The problem is for North Korea, we have no calibration. We have not personally gone into the site, set off a known explosion with a known size and measure its magnitude. So there's a lot of uncertainty in what is the predicted magnitude for a given size event at North Korea. So we're confronted with the problem that we were originally confronted with in the 1980s with the Soviet Union, where we did not have known confident yields. We had to deduce what was the appropriate magnitude yield relationship to use to estimate their compliance with, at then, the threshold testband treaty. The problem is that if you have an explosion in one region, say on the Soviet region or in the Nevada test site, the magnitudes can differ because the transmission through the Earth is different. And it will depend on whether the upper mantle around the site, what type of rock is there, and what type of attenuation may dampen down the sound as it goes through the Earth if that happens. Such that there would be a difference for the same size explosion in the Soviet Union or the Nevada test site, you'd get a difference in magnitude of 0.2 units or so. That's important because that's on a logarithmic scale and it implies very different yields. For example, for this 2017 event, the measured estimate of magnitude from the USGS using 900 observations around the world is 6.3. If you plug 6.3 into the magnitude yield relationship from NTS or into the magnitude yield relationship from the Soviet test site, you get very different estimates of how large the explosion is. So we have to calibrate the site, okay? So how do we go about doing that? We have to go back and utilize the methods that we applied in the original case, where we determine what is the transmission of the waves through the Earth to figure out what is the appropriate magnitude yield relationship to use. And we know that the testing in North Korea is in a mountain. This is looking down on the mountain. This is the peak. This is where they tunnel into the side of the mountain, and you go horizontally at some distance into the mountain. And we're not sure how far they've gone. So we don't know how deeply buried the explosions are. So we have to determine that because the depth of burial influences the pressure on the explosion, which will control how much of the energy comes out in the sound wave. So we have to determine the explosion yield and the depth together. They're both coupled together, and these are problems that we can do only seismologically with any confidence, I believe. It's difficult with other methods. Well, this event was recorded around the world. The event's located here. These are just some of the open stations. This includes some of the IMS, or international monitoring stations, that were put out explicitly to be monitoring for nuclear explosions. You'll hear about more of that network later. This is openly available stations that you can download freely. And what you're seeing here is just a recording as a function of time of when the sound wave gets to different stations. You can see it's a simple pulse. Simple pulses are things that we can usually model pretty well. We've developed a lot of capabilities over the past decades to solve the problem for an explosion embedded in a layered Earth and how the waves will propagate through the Earth, reflecting off the surface and being attenuated as they go. So we can model these or predict what the waveform should look like for specific values of the yield and specific values of the attenuation. And for example, here, the black line is the observed data stacked of many stations compared with red line where you're matching the amplitude and the waveform for a specific yield and a specific attenuation. You are calibrating the test site for this event to give you the right yield, determining what the attenuation is, not assuming that it's the same as at NTS or the Semipalatinsk Soviet test site. That's important because we're trying to narrow down what range of numbers you get. Unfortunately, it's not totally unique. There's a range of attenuation parameters on the vertical, a range of yields that will give you good match of the amplitudes. On this side, it's good match of the waveforms. And we look at the intersection of the blue areas where the darkest blues overlap. This is the region that fits the amplitudes and waveforms well. And it gives us an estimate of what the attenuation parameter would be and what the associated yield would be. And for this 2017 event, our estimate is that it's around 220 kilotons, but with a big uncertainty, plus or minus 80 kilotons. And that's respecting the fact that there's a trade-off in the modeling procedure and some uncertainty in the choice of the parameters for modeling the event. But seismologically, this is what we have to do. We have to do this calibration with some confidence before we can turn an MB measure into an estimate of the size of the event. Once you have one event calibrated, then you can then deduce by methods that I spoke about yesterday, and I won't go into the details here, to measure very precisely the relative yields of the other events. But now you know one The relative yields give you yield estimates for the others, and that's what's indicated here. So this largest event, 220 plus or minus 80, for the events that have happened over the past 10 years, we get estimates of what their absolute yields are, having calibrated the site, and we're no longer dependent on translating an MB yield relationship from another site. We're doing it specifically for the North Korean test site. So this is one of the critical applications of seismology to get the yields, in addition to identifying the explosions. So thank you very much.
Good morning, everybody. My name is Tormod Kverna. I'm head of research and development for seismology and test plan monitoring at NORSAR. NORSAR is the Norwegian data center for technical matters related to the Comprehensive Nuclear Test Ban Treaty. And we are operating several worldwide large arrays. And the one you see to the right here is the NORSAR array, which came operational in 1971. And has recorded through the history a large set of nuclear explosions. And what you see here are the observations at these stations of the 6 DPRK nuclear tests. And as you are all aware, the tests now in September this year was exceptionally large as compared to the other ones. The network of seismological observatories can be used to accurately locate these events in North Korea. There are no local stations, so we have to rely on observations on a global scale. So what you see here on the figure up in the corner is the local stations nearby North Korea, in Japan, in South Korea, in China, and Eastern Russia. And if you take the recordings at the station in South Korea and align them, you see that the 6 events, they align very well. But if you use the same alignment for the station in Eastern Russia, from to the right here, you see a deviation. And this deviation can be repeated on all the global stations and measured. And based on this information, you can come up with a very accurate relative locations among these events. And of course, you can place this pattern of relative locations whatever you like, but if you use the infrastructure and images, you get a fairly good idea on how these events are located, even though you have stations as far as several hundred kilometers away from the recordings. So in this way, we can use seismology to put very strong constraints on the accurate location of these events. In addition to the large nuclear tests that has been conducted this year, there are a series of smaller events observed at this test site. And this is, of course, of interest to get a kind of information on when they occurred, how large they are, where they are. And if you look at the figure to the right, there are the 6 nuclear tests are shown by these radiation signs. In 2014, there were 2 small events observed. The same, just 2 days after 2006 event, there was a small event observed. And just after the event this year, there was a rather large aftershock, which have been discussed today to be a collapse inside the source area. But in addition to this, there have been several smaller events observed that we are not that cannot be located very accurately, but they are at least nearby or close to the test site. So we have been doing analysis on the different signals here and trying to see what's going on. And what we have found, at least through the analysis, what we call cross-correlation by matching the waveforms from previous events to the new data, is that there is a rather large set of new smaller events occurring at the test site now in December. So this has been extensively studied during the sessions today, at least, and there have some conclusions on that, or at least some initial guesses on this. But to summarize, the 6 nuclear tests, of course, they have been recorded worldwide, and there are a lot of stations. We have managed to make quite accurate relative location estimates for these explosions. However, this 3rd September has a relatively somewhat more uncertain geolocation because of the large size of the lower frequency of the waveforms. Several stations, additional events have been located close to the test site. between 2014 and 2017. Two of these followed shortly after the largest two nuclear tests, but they show very different waveforms from those from nuclear tests, so they have a very different signature. The two events in 2014 show great similarity with the events occurring in the time period late September to December this year. And again, the correlation analysis reveals that there is a significant increase in the number of events close to the test site this year, but the location and course of these events are currently being investigated by several groups in the community. Thank you.
Good morning, everybody. My name is Jeon, Senior Research Scientist, KMA. September the 3rd, I think that's in U.S., it's a Labor Day weekend. And I was just, coming back from the Vienna for joining the meeting. I was enjoying the whole, Sunday afternoon. But, that's in local time, September 3rd, 12 o'clock, 29 minutes, North Korea, the test for 6th nuclear test. So we had, on that day, had media brief at 15 o'clock at KM headquarters. So because we had only 2.5 hours, everybody going back to the office and prepare for the media brief for this, test site results. So because we had only 2.5 hours, our media briefing content is very simple. We just, explain the characteristic analysis of North Korea signals, and we just showed that. I will just explain, what we did on the media briefing and the role of KMA. KMA is a government organization, has a sole responsibility of issuing official analysis result of earthquake, including a nuclear explosion, to the public, media, and the bylaw. So we all has a responsibility for nuclear test in Korea. So we using absolute, analysis for estimating the North Korea test site, and this is our location analysis result for previous 6 tests, because we using local network to analyze the detection of North Korea nuclear test. So if you see the cartoon on the left side, the explosion, if the earthquake explosion occurred, earthquake, wave generated, but nuclear explosion or could generate infrasound wave. That's infrasonics waves generate through the air. So the seismic station and infrasound station detect infrasound wave and the seismic wave. So we analyzed both signals to detect North Korea test. The first, waveform comparison. So this all traces recording at station SEO2 located at Seoul. So, and this is from the 2nd to the 6th waveform, showing that for 5 preceding tests. The 6th test show much larger, peak amplitude compared to the rest of the 4, and the rest of 5, event. And for the spectral amplitude, studies of the Seoul station show that if you see all the spectral amplitude ratio, it has the peak at spectrum at 2 Hertz. And if you see the ratio for the 6th test and the 5th test, if you compare that, you will see that at low frequency range, the amplification is show higher compared to the high frequency range and compare with the previous test. So high frequency energy, rapidly fall off after 2 Hertz, and that was this founding led us later we study new magnetic scale. And the second, spectral amplitude ratio comparison is we using PGLG, mostly discrimination of to compare and to discriminate the signals. So if you see the left, the normally earthquake has bigger S-wave amplification. So the logarithmic number, the ratio is less than 0. And if you see the explosions, the P logarithmic scale for P over S number is greater than 0. So very simple, criteria we use to, discriminate to spectral ratio for fifth and the sixth explosion test that they're using for this. And the black line is the spectral ratio for explosion, and the green line is the earthquake, natural earthquake generated near the test site a long time ago. And this is very distinct mark, very different for the frequency range between 2 to 10 hertz. You can see that these two spectrum is isolated and separated, so we know that this is nuclear test. And the moment tensor solution is also indicating the sixth test show a very large ISO, which indicate explosion as very big, volumetric compressions. And the right side cartoon show that the mechanism, focal mechanism is explosion is like this way. So for third, fourth, fifth, and sixth test all show the explosion result. And the infrasound analysis result. Nuclear explosion, at the test site and the mountain mountaintop, after the explosion occurred, it just uplift the mountain area and fall down. Then it started to generate infrasound. So if you see the waveform, infrasound waveform here in the two stations at KMS station, that it is recorded durations of the where infrasound waves is recorded more than 1 minute for two stations. It's highly long duration compared to fifth test. And azimuthal, direction detected indicate the fifth test and the sixth test indicating the North Korea test site. It's slightly different. The azimuth angle is different. That's because of maybe the atmospheric, wind effect, I think. And finally, as I said that before, because the high, low frequency energy content lead us to restudy of our revised magnitude. So, and for sixth test we got 6.08, and for fifth test we got 5.03 magnitude. And if we compare it to IDC, magnitude, we is almost compatible with their result. Thank you.
Good morning. My name is Jolanta Kuśmierczyk-Michulec. I'm Atmospheric Sciences Officer at IDC. I would like to give you some brief information about the methods that we are using that are related to IMS radionuclide monitoring. First of all, I would like to emphasize that the moment CTBTO's monitoring stations pick up an unusual seismic event in the DPRK, on top of routine operational radionuclide monitoring, special efforts were undertaken to make sure any possible signal from a release following this event would be captured, analyzed, and that state signatories will be informed in a timely manner. So the international monitoring system developed by CTBTO is a global system of monitoring stations using 4 complementary technologies: seismic, hydroacoustic, infrasound, and radionuclide. And here is the map showing the location all stations: seismic, hydroacoustic, infrasound, and radionuclide. But I will focus on radionuclide stations, and for your convenience, I just highlighted by yellow dots those stations. The radionuclide network includes 80 stations, out of which 40 are to be equipped with noble gas systems. And the aim of radionuclide station is a global monitoring of radioactive aerosols and radioactive noble gases, supported by the atmospheric transport modeling. I would like to present you the closest network of station of IMS radionuclide stations. In 2017, it was related to DPRK event. So the closest network includes 9 particulate stations that were sending data, and 5 noble gas stations that were also sending data. So it's a kind of a subset of the whole global network. In our operational work regarding atmospheric transport modeling, we operationally do simulations for in a backward mode. We use Lagrangian dispersion particle model, a FlexPart, and the backward modeling, it's for all stations. So it means it's the release point is at the receptor's location. So if an IMS station detects an elevated level of radionuclide, the ATM in a backward mode helps to identify the origin of the air masses. In special cases, like for example DPRK, or in the past it was the case of Fukushima, we do also forward simulations from the location of the waveform event. So the purpose of forward simulation is to predict which of our IMS stations may observe radioactive release, and it helps also to verify and validate hypotheses. So here is an example of forward simulations that corresponds to the main event. The release is on the 3rd September, and it shows the transport of air masses during 7 days. For that simulation, we used NSEP forecast data. The air masses provide also the link between radionuclide release that is observed at IMS station, and also the link between radionuclide release and radionuclide measurements. And in case of single detection, we use a concept of field of regard. So it means we look at the backward trajectories, trying to identify the source. But in case of multiple detection, for example, one station has a number of detection, or there are several stations which detect the same isotope, we use a concept of a possible source region. In more advanced, we have several other methods related to possible source region, so depending on what is detected. So possible source region is just the method, and that for each grid point in space and time, we calculate the correlation coefficient between the measured and simulated activity concentration, simulated using atmospheric transport modeling. So here on this plot, it's an example of PSR. It's just a snapshot for real detection, and this is a snapshot for 26 September. For 2 samples of detected at Japanese station Takasaki and 1 station in Hawaii. This PSR is generated for xenon 133. In case we would have, I need to mention that in case we would have a second isotope, the information would be more certain. So the color code shows different correlation coefficient. It means different probability, and the relatively high values of PSR indicate for DPRK. But also indicate for potential sources in other areas. So it means this is kind of tool, PSR is a kind of tool that helps to indicate some area and also indicates time constraint, but to really make some kind of definite conclusion, we always need to verify other hypotheses and have other information. So to summarize, no CTBT relevant radionuclides were detected by the IMS that could be unambiguously linked to a nuclear test in DPRK. ITM products greatly help interpreting radionuclide observations, identifying possible source locations, time, and intensity. I need to mention that each event, like we compare different DPRK events, each event is different. So there is no really, so it has to be considered in the individual way and requires a specific approach. Whenever elevated concentrations of radioxenon were detected, they were investigated. But were not conclusive with regard to a possible association to the seismic event on 3rd September. So now in December, 3 months later, the chances to still observe late release of radioactivity are decreasing. With this statement, I would like to conclude. Thank you.
Okay, we will now take questions from reporters in the audience. Just a reminder that only reporters can ask questions. Please state your name and affiliation.
Hi, Sid Perkins, freelance. I have a question for you, Dr. Lay. You showed the analytical technique you used to look for the magnitude and the error bars on the most recent event, and then you used that to calibrate, the other events, and you showed the magnitudes and error bars for those. Has the information from the new test significantly changed the magnitudes and error bars for the old tests, or did it kind of just reconfirm what those sizes and error bars were?
Well, it's a little bit difficult to compare my relative measures because they're not magnitudes, but in a general sense, no. The procedure I used to get the estimates for the smaller events, I didn't go into details, but it actually determines how deep they are. So I'm correcting for that, which is not done with normal magnitudes, and I'm correcting for how the specific yield of each event changes the shape of the sound that comes out. So it's a little bit more quantitative. The relative sizes behave very similarly to magnitudes. So the magnitudes are not strongly biased. It's more the setting of the absolute scale that is gained by the modeling that was done. And the numbers still there are comparable to what was obtained using the Soviet testing site as an analog and using its relationship. They're pretty close, but you're just not sure when you're doing that, and so we gained some confidence. But the numbers did not change in a dramatic sense, and they still have large uncertainty.
Are there any other questions from reporters in the room? Are there any questions on the chat? No? Any other questions? Okay, that concludes our press conference. Thank you very much. Next up at 1:45 is a media availability with Vaughn Tarakian.